My name is Mr. El-Karyani. I'm going to be your physics teacher next year. I'm going to make a video to help you work with the summer assignment over the summer. And I'm just going to go over, not all over the whole summer assignment, but I'm going to go over some of the ideas in summer assignment. And I'm going to do this briefly. So the first idea is going to be solving some type of equation. So if I have 4ax, okay, equals 2bx plus 6, let's say. And we want to solve for a. In other words, we want to isolate. When I say solve for a, I mean isolate it. So how do we do this? A lot of times people, what they do is they say, oh, there's an x on both sides, so I'm just going to cross it out. So what we need to do here is we have to do a is equal to 2bx plus 6 divided by 4x. Now we can maybe reduce this because there is a 2 common to every term here. So this is just going to be bx plus 3 over 2x. So you cannot cross out these x's, right? Because there is no x with the 3. So that's one idea. And I'm going to do this quick. So the other one that I want to talk about is solving quadratic equations. 7t minus 4t squared equals 0. And the other one that I'm going to do is negative 22 equals 6t minus 5t squared. When you're looking at an equation like this, you can factor out a t, okay? And this is going to be 7 minus 4t left in there equals 0. Now, if a product of two things is equal to 0, one of them has to be 0. One of these terms has to be 0. So t equals 0, or t is 7/4, okay? For this one here, if you want to solve it, maybe you want to write it as, or actually, let's keep the quadratic term positive, so I'm going to move everything to the left side. Minus 6t minus 22 equals 0. And you would do a quadratic equation. One word of advice is don't try to factor in physics because numbers are not always nice to factor. So here you would just do your quadratic equation and solve it. And here you should have you could have two solutions, you can have none, and you can have one solution. All right. The next thing will be we're going to try to solve for variables. So we're going to solve I equals v over r for r. Okay. So that's what we're going to try to solve. Now, how do we do this? Well, so I want to isolate r. So I can say that r equals v over I. I hope everyone sees that. Okay? If you can't see stuff like this, you should brush up on your algebra skills because we're not going to show you how to do this. This should be able to do this pretty quickly. Now, a couple questions. All right, so I'm going to have this equation again, v over r. Now, what happens if r doubles, right? What happens to I? In other words, by what factor does it increase or decrease? Well, if r increases, and obviously I'm keeping v constant, so if v stays constant, if r is doubled, I has to go down. How much does it go down by? It goes down by half. So in other words, I is half as much. Okay. The next thing we're going to do is we're going to solve some trig equations. So if I have a right triangle, if it looks like a right triangle, then it is a right triangle. I'm not going to put the symbol there. So if this is, let's say, this angle here is theta, okay, and we're trying to solve for this angle here, we call it x. Actually, let me make this 30 degrees. All right, and I'm going to make this 5. So in order to solve for this, you're going to use your SOHCAHTOA. So with respect to the 30, the x is the adjacent, and the 5 is the hypotenuse. All right, so here I think we have to use the cosine of 30 equals x over 5, and you know what to do from this. So x is 5 cosine of 30. Okay, and one way of knowing that at least you're on the right track is like x has to be less than 5. This is the hypotenuse has to be the longest leg. Let's try to do something like this. So let's make this a 1. Let's make this angle theta, right? So if I want to find that theta, actually, I'll change it up a little bit. So I'll make that 1. So if I want to find theta, it looks like I'm dealing with the opposite and the hypotenuse. So I have to do sine of theta equals 1 over 5. Okay? Now, how do I solve this? Well, theta is the inverse sine of 1 over 5. Now, you should have done this in your math class this year. If you haven't done it, if you just go to your calculator and make sure you're in degree mode, otherwise, if you're not in degree mode, the angle that's going to be given is going to be in radians. And just type in second sine, that's what you see, the sine negative 1, and put in 1 over 5, and it will give you your angle. Okay. Scientific notation. So if I have to do 5.2 times 10 to the negative 5 over 7.3 times 10 to the negative 2. A couple things you have to be careful with here. Actually, I'll make this simple here. So I'm going to say 10.4. I don't feel like doing the math. So 5.2 divided by 10.4, that's 0.5. We'll leave it like that for now. Times 10 to the what? So we have to subtract negative 3. That's not in scientific notation. Okay? So we have to make that 5 times 10 to the negative 4. If you're going to do this on the calculator, okay, you make sure that you put this bottom part in parentheses. Because if you don't do that, what's going to happen, you're going to take this top, you're going to divide it by 10.4, and you're going to multiply by 10 to the negative 2. In other words, the calculator just does PEMDAS. All right. So I think I talked about the division in the calculator. Be careful with the parentheses. Now, I'm going to give you an equation here. F equals K, Q1, Q2 over D squared. And we're going to solve for K. So I'm going to do it for different things. I'm going to solve for K, I'm going to solve for Q1, and I'm going to solve for D. Okay? So how do we do this? Well, if I want to solve for K, it means isolate K. So I have to multiply both sides by D squared. So K is going to be equal to that. And divide by Q1 and Q2 by that product. If I want to solve for Q1, I do the same thing. F D squared over K Q2. Now the tricky part is that you have to be super careful about how to solve for D. So D will come up here, D squared will come up there, F will come down there. So this is what we have. D squared, I'll do it slowly. F Q1 Q2 over F. Now, if I take away this square, I'll have to do plus or minus. Now, in physics, we don't pick both of them, or at least for most of the parts. Sometimes we do. If this D represents something that physically cannot be negative, like time, for instance, or distance, then you have to only pick the plus. If it's other things, which is like an electric charge, and you guys learned that the proton is positive, the electron is negative, then if that's a charge, then it could be either plus or minus, if we don't know whether it's an electron or a proton. Now, in this equation here, what happens to F if D is tripled, multiplied by 3? Well, if you notice here, the D has a square, which means the 3 will be squared. So F will be 1/9 as much. I hope you can see that. All right? I'm going fast here because these are skills that you should already know from your math classes. Now we're going to try to convert from meters per second to miles per hour. So I'm going to just throw a number in there. 30 meters per second equals how many miles per hour? Well, you guys do the, dimensional analysis. So 30 meters in 1 second. All right, so I want to get rid of the meters, so I put them down here. I put the miles up here. I want to get rid of seconds, I put them on the opposite side. I put the hours here. Now then I make a decision. What's bigger, a mile on a mirror. You might have learned this differently in chemistry. So, but this is how I do it. I say, okay, a mile is bigger, it gets a 1. The meter is about 1,600. I mean, a mile is about 1,600 meters. It's about 1,609, but we'll go for 1,600. An hour is bigger than a second, obviously. An hour is 3,600 seconds, not 60. That's a common mistake. And you would just multiply the top, multiply the bottom, and divide. Right? You should be able to do the same thing if you're going from, let's say, 20 miles per hour to meters per second. Same thing. Okay? Same process, in other words. Okay. So the next thing I want to do is I want to solve an equation 5 minus 2 cosine x equals 8 sine of 30. Now how do I handle this? Well, I can subtract the 5 to the other side, so negative 2 cosine x equals 8 sine 30 minus 5, which really is equal to negative 1. Sine 30 is half. All right, so this cosine of x is going to be equal to 1/2, positive 1/2, which means x is going to be equal to the inverse cosine, which is in your calculator, of 1/2. And that should give you something. And I think that something, if I'm not mistaken, is 60, I believe. All right. The next thing is we're going to solve, well, no, I'm not going to solve. So here's an expression. U equals 1/2 kx squared. Okay? Now, if k is tripled and x is halved, okay? What happened to u? What's the new value of u, in other words? By how much does it change? By what factor? Not by what addition. So if k triples, this becomes 3 times as much. But if x doubles, is half, this becomes 1/4. So now this becomes 3 and 4. So the u would become 3/4 as much. Okay? All right, we're going to solve an equation. 1/10 equals 1/x plus 1/5. Now, how do we deal with this? Now, there are a lot of ways to deal with this, but I'll show you the easy way. Some people like to get rid of the fraction first, but for me, I don't care. So I'm just going to subtract the 1/5 here, okay, equals 1/x. So now, that's going to be negative 5 over, no. So we can do a common denominator quickly here. So this is 10, this is 2. So this is going to be negative 110 equals 1/x. Since the tops are equal, the bottoms have to be equal since the fractions are equal. So x is basically just negative 10. I mean, you can do it in any other way you want, but this is probably the quickest way. All right. All right, one more thing about the relationships. V is IR. Okay? I did that earlier. Now, what's the relationship between I and R if V is constant? Okay? All right, so if V is constant, I and R have to vary inversely, because if I goes up, R has to go down by the same factor, in other words. So if I doubles, this has to be cut in half. If this is 4 times as much, this is 1/4. So this is an inverse relationship. That's what we call an inverse. So if one goes up by a certain amount, not a certain amount, by a certain factor, the other one will drop by the same factor. All right, so if we keep, what's the relationship between V and R? No, V and I. If R is constant, if we keep R constant. Well, if R is constant, V and I have a direct relationship. In other words, this is not changing. So if I goes up by 2 folds, V will follow the same amount, same factor, by the same factor. All right. Now I'm going to talk briefly about graphing, and I have a graph paper here that I'm going to bring up on the screen. All right, good. Okay, and I have some data that I want to graph. And my data is VI 0, 0. I'm going to put 2, 3, 5, 6, and 8. Okay, and here I'm going to put 6, 9.2, 14.5, 19, and 23.6. And you can see pretty much that it's linearish. Because each time I multiply the i's by 3, I get about V. We're always going to put the independent variable here, in other words, the x, and the dependent, which is the y, in there. So I'm going to come to my graph, and I'm going to try to do this quickly. So here's my x-axis. You're going to do this with the ruler, obviously, right? And here's my y-axis. And use up all the graph that I give you. So let's say my graph paper kind of like stops right there. That's it. I don't have anything more than that. So I'm going to see what scale to use. So what do I have here? In here I'm going to put I, and you would put the units, depending on what the units are, okay? And I'll just change this, okay. And here we're going to put the V, and you're going to put the units there. So whatever the units are. And in V, the highest value you're going to need is about 24. So I would count how many boxes I have. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 17, 18, 18, 19. Okay? So I need 24. So a good scale, how about if we do for every 3 boxes we do, or every 2 boxes we do 1? No. For every box we do a 2. So, or for every 3 boxes we do a 2. So let's see if that works. Actually, no. We'll do for every 2 boxes a 3. Let's see if that works out for us. So 3, 6, 9, 12, 15, 18, 21, and 24. It works out pretty good. So I'm almost at the top of my graph, and that's what you want to do. Now, how do we do that? Well, we take the highest value that we want to have, which is about 24, and divide it by, I forgot what I said, 18, I think, right? So 24 divided by 18, let me take out my calculator. 24 divided by 18, which means that each box here is going to get about 1.33. So you always want to go up. So I'm going to make every box 1.5. That's the closest nice number to 1.33. So now we're going to start graphing. Actually, we have to do this side here. So in here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So I have 8, and I have 22 boxes. So 8 divided by 22, I'll make it actually 20. I don't have to go all the way to the end. So each box is worth 0.4. So which means 5 boxes are worth a 2. 1, 2, 3, 4, 5, so that's a 2. Right? 1, 2, 3, 4, 5, that's a 4. That's a 6, 2, 4, that's an 8. And we got our graph. We have to give it a title. So it's I versus V. It's always the dependent versus the independent. Remember that. Okay, so when you're labeling your graphs. Now we're going to start. So Z passes through 0, 0. You know what? I should have done it yeah. I wanted to do I on this side and V on the other side. Sorry. So just flip this. Sorry. And so this is going to be, you know what? I'm going to keep it as is. And I'm going to just change this here. Things happen, so I'm just going to have to change it. Yeah, the I has to be here. Okay? And the V's have to be here. So I think I have the same number of boxes. So I'm going to try. So 3, 6, 9, 12, 15, 18, 21, 4. That's good enough. Okay. We could have done better, I think, but that's fine. For now, I just want to show you the ideas. So for here, I think we're gonna go for every 5 boxes is a 2. We said 2, 3, 4, 5. I think it's gonna be short. All right, so I'm gonna go every 4 boxes is a 2. 2, 4, 6. That's better. Okay. Sorry about that, but all right. So here we're going to put the v in the units. So let's graph this. So it passes through 0, 0. All right. When v is 6, I is 2. So it goes through here. When v is 9.2. Okay. So now this is a 10. This is a space here is what? 3. So 9.2, so basically we have 2 boxes for 3 units of V, 2 boxes, and we want to know what's the equivalent for 9.2 units, so how many boxes we need for that. So if we solve that proportion, we should get 9.2 times 2 divided by 3, okay, so 6.13. So from here I have to count 6.13, 2, 4, 6, so I'm almost like right there. So that's going to be 9.23. 9.23 right there. Okay, and then we do 14.5. So that's 14.5. So we need to make 14.5 here. So it's 14.5 times 2 divided by 3. So it's 9 2/3. So 2, 4, 6, 8, 9 2/3. So that's 14.5. That corresponds to 5. If I can see this, that's 4, that's 5. Okay. 19, which is 18, that's 21. So if I put a 19 here, so I have to take 2/3 of 19. So that's 12 2/3. So 2, 4, 6, 8, 10, 12, 12 2/3, and that corresponds to 6. Corresponds to here. Okay. And the last one, I'm going to do 23.6 times 2 divided by 3. So that's 15 3/4 about. So 15 3/4, 2, 4, 6, 8, 10, 12, 14, 16, 16 and 15, 15 3/4. So 15 3/4 is here, and that corresponds to 8. That's going to put me up here. Okay. Now you take a ruler. Okay, let me grab a ruler. I'll be back. All right, I'm back. So we're going to take a ruler. We're going to draw a line of best fit. Now, a lot of people make a mistake by connecting the first point and the last point, but that's not true, right? So you have to do a line that kind of like averages all the points. So in other words, you have to leave an equal number above as under. Or if you're going to leave some points above, the number of points above has to be equal to the number of points under. So let's just say, I'm just saying it looks like that. This is not probably accurate, but let's just say that's what the equation looks like. Right? So make sure you don't make that mistake connecting the first and the last step. So in here I want to talk about a couple things. So we talked about the independent being here, the dependent being there. We label the axis, we put the units, we draw the line. If the line does not look like it's linear, don't draw the line of best fit. Take a flexible ruler, right? ruler, a bendy ruler, and follow the shape of the curve. Okay. If it looks like a parabola, draw it as a parabola, right? If it's a square root, draw it as a square root. All right. So now we're going to talk about interpolation and extrapolation. So let's say the question is, actually maybe we should write the equation of the line. Let's do that. Let's write the equation of the line. So the equation of the line is going to be y, which is I, equals, so in other words, it's going to be y equals mx plus b. b being the y-intercept, goes through 0, 0 in this case, so this is gone. The slope we don't know, and x is played by v. Okay. So let's see if I can find the slope here. Do not, whatever you do, do not just pick points from the graph, from the table, and put them in that equation. The points have to be from the graph itself. So usually what I do, I pick points that cut at a corner, and the reason for that, because they are easy to read, usually. So I'm going to pick this guy here that I circled, do it in a different color so you can see it. So I'm going to pick this point here, and why not 0, 0, since it passes through 0, 0. So the slope is just rise. So this is 7, that's 7.5. Oh, I'm sorry, it reaches up to 8. Or did I miss that? Oh, that was supposed to be down here. Let's just say 8 is up there, but it doesn't matter. Yeah, I missed that. So let's say it just reaches up to there. So it's going to be 7.5. Let's just say this is 7.5. I didn't see that I made a mistake. Over a run of, this is going to be, if this is 21 and this is 24, this should be 22.5. And that's your slope. So 7.5 divided by 22.5, that looks like it's 1/3. Okay? My slope should be a little less. This should be leaning down because I missed this point. This point should be down here. Okay, so my equation now looks like this. I equals 1/3 V. Okay, now we're going to talk about interpolation and extrapolation. Interpolation means you need to find information from the graph from within the data that you have. Okay, so let's say the question is, well, find the I when V is equal to 10. Or actually, I'll make it simple, 10.5. Okay? So when V is equal to 10.5, I'm here. So all you have to do when you deal with interpolation, so you are within the data. That's why we call it interpolation. And you come across, hit the curve, come across, and read what that point is. So that's, what is that? That's 3.5, and maybe a fifth of that. So that's about 3.6-ish, sounds like it, right? Okay, so I is equal to 3.6. Now, if we put it in this equation, we should get the same thing. So if I put in, what did I say, 3.6. Okay, so if I do, if I do 10.5 divided by 3, I should get about 3.5. So that's close, right? That's where we are. Okay. I remember that that's not 1/3. I'm off a little bit there. Extrapolation would be questions like, okay, well, find the voltage V when I is equal to 20. So if I have to deal with that, I have to make sure that I read the whole question and make sure there is no questions like this, or read the whole problem. Because if there is, I have to make my scale so that the 20 fits in there. If the 20 doesn't fit in there, I have a problem later. So always read the whole problem before you answer this. Since I can't do it there, I'm stuck, right? So, but I can do it for a point that's already there. So if I try to do it for 9, let's say, 9 is up here, right? all I have to do is go across, okay? Which means here you have to kind of like extend your line, go across and come down and read the value for I. You can also do it with the equation, but if it says interpolation or extrapolation, that has to be done graphically. So we did all that. All right. So I'm going to try to do one where it's not linear. All right. So let's say we have to graph equation y equals 5x squared. All right? Or better yet, let's just say we have data. We have x here, we have y here, we have 0, 0. We have 1, 5. We have 2, 20. We have 3, 45. We have 4, what is that, AD? Yeah. We have 525. Let's animate nice numbers because I don't want to deal with the decimal fractions at this point. So let's say you make your graph, okay? Here's your x and your y axis, right? And you only have that much to work with. So the x will go down here and the y will go here. So maybe every box is a 1, 2, 3, 4, and 5. We could have gone with more, but that's fine. And here we can go maybe, we can go by every 3 boxes is a 20, it looks like. 20, 40, 60, 80, 100, okay? And this is 120, and this is 140, okay? And so we're going to graph this data. So 0, 1, 5. So now I have to figure out this is 10, this is 1, 5. This is 220, 220. 3, 45. 3 is 40. I messed this up. I should, okay, you know what? Let me just put this at the bottom here. Because I messed up with the scale here. So 0, I say 1, 2, 3, 4, and 5. Okay, let's do it again. 1. Now 5, what is that going to be? So that's, this is 10. That's half of 10, so it's about there. So 2, 20. 3, 45. So this is 50 and half of that, so it's about there. 3, 45. 480. 480 is here. And 5, 125. So 5, 120. Okay, so that's 130 right there. So it's about 2/3 of the way it looks like. So we're here. So now this does not look linear. Don't force it to be linear. Right? In this part it looks linear, but here it doesn't. So you have to take one of those flexible rollers and you have to kind of like curve it, bend it until you see this. Right? It doesn't have to go through all the points. You might miss a point here and there. So now, if you look at a pattern here, you're going to see that the numbers on the right are basically nothing other than the numbers on the left squared times 5. So here is your pattern. Okay? Now, we're going to talk a little bit about linearization, which is one of the hard topics in graphing. So now, what happens if I make this x squared my variable? It's not x anymore. So in other words, I'm going to call this big X if you like. So now it's going to look like y equals 5 big X. And I'm going to plot the big X on the x-axis. Right? So my x here is basically, or I'll put it on the other side since it's closer to here. My x basically is all these guys squared. Okay? And down here, this is going to be x squared down here. And this is going to be just y. And you would put the units, you put y versus x squared. Now, looking at this, we should get a linear fit here. It should be linear. It should be a line. Right? Sorry, I didn't know you couldn't follow what I'm doing here. This thing is All right, so, okay, so now you can see what I was talking about. So if I can do 0, 0, which is right there. I can do, but I have to actually make a scale here. So how about every 2 boxes as a 4? Let's see if that works. 10, 12, 14, 16, 18, 20, 22. No, this is 12. A lot of mistakes there. 16, 20, going too fast. 24 and 28. So skip, forget about the other stuff. All right. So 0, 0. Then we're gonna go 1, 5. So 1 is here, 5. 4, 20. 9, which is, so is that 8? So 9 is here. 45, and I think we said 45 was about there. Yeah, because that's 50. Yeah. And 16, 80. And 25, 125. So 25 is about here. If I go up, 125 should be there. Now you can see that's a line. All right, that's what we call linearization. So this is a line with a slope of 5. Okay? All right, last thing I want to do is, all right, so if I do, and I'm not going to graph this, if I do t equals 2 pi square root of m over k. If I graph this, if I put in t here and m here, from your math class, you should see that this is going to be a square root function. K is a constant, in other words. In other words, this can be written as 2 pi over square root of k, square root of m. M is the variable, t is the variable. So I should expect something like that, which is a root function. So that's a square root function. If I change one thing, and instead of graphing t in terms of versus m, I graph it versus square root of m. Just like before, this becomes my new variable. Let's call it big M. I should expect a line. What's the slope of that line? Well, it's just going to be that. So in other words, this is going to be t equals this expression times big M. And big M is this here, right? So this is just like y equals mx. So the slope is 2 pi over radical k. All right, one last one.